And now that we know how to learn and classify with a single perceptron, let's make things a little more interesting. Let's put a few perceptrons together to get a two-layer perceptron network. We'll start with this perceptron, then add a few more perceptrons here. Now let's take the output from these perceptrons on the left and feed it as input to our perceptron on the right. We get a two-layer perceptron network. Now let's assume that the input to the three perceptrons on the left is the same feature vector. We can redraw our perceptron, as shown here, with the same feature vector f of x being fed to the three perceptrons in the first layer. Now the output from the last perceptron on the right will depend on f of x, but it will also depend on the weights. We'll put all these weights associated with the different perceptrons in a single weight vector, w, and we'll say that the output depends on w and on f of x. Now we still have to learn the weights from our training data. So let's say we have m training examples, x1 through xm. Each training example has a training label associated with it. So y1 through ym are our training labels here. Our weight vector contains all the weights associated with all the perceptrons in our network. Our goal is to find the weight vector that minimizes our error. So for each example, xi, the error is the difference between the training label, yi, and our prediction. This is the output from our two-layer perceptron. We called it hw of f of xi. So we need to find the weight that minimizes the total error over all training examples. The error is the sum over all examples of the square of this difference. The question is, how do we find the value of w that minimizes this error? The answer takes us to a technique that we introduced at the beginning of this course, and that is hill climbing. Except that here, since we are minimizing our objective function and not maximizing it, we call it gradient descent. So here's a refresher on our hill climbing algorithm. We start our search anywhere, and we try to move to the best neighboring state. A better state is a state that gives us a better value for our objective function. If there is no better neighboring state, we quit. We return the state that we're at. A neighboring state is a state that we get to by varying our weight vector w a tiny bit. So what's going to be our challenge here? What was the problem with hill climbing? Let's take another look at the two-layer perceptron network here. Each of these perceptrons produces an output when the activation exceeds a threshold. Remember, the activation was the weighted sum of the features. So we can model the output of each perceptron by a step function. The output is 1 on one side when the activation exceeds the threshold and 0 on the other. The problem here is that small perturbations of W are unlikely to have any effect on the output. That means that our gradient descent will be stuck on a plateau, on a local minimum. The solution is to soften the threshold function and approximate the hard threshold with a continuous function. The logistic sigmoid function is commonly used. Instead of an abrupt transition from 0 to 1, we have a more gradual transition. When we replace our step function with a logistic sigmoid function, we get sigmoid neurons. We have an input layer. The neurons in the middle make up our hidden layer, and the neuron at the end, whose output is the combined output of the network, makes up our output layer. Now, we could use other activation functions. The logistic sigmoid function gives us the soft threshold between 0 and 1. The hyperbolic tangent gives us a transition between -1 and +1. And the rectified linear unit function, ReLU, is also used, and it gives a transition between 0 and positive values. All of these are valid activation functions that are commonly used. So here's what we have now. The input layer takes in the feature vectors and passes them to the network. There is no computation in the input layer. The hidden layer performs some computations and transfers information to the output layer. The output layer takes in information from the hidden layer and performs some computations. It's actually responsible for generating the final output of the network. Its output is the combined output of all the layers. Note that when we have a single neuron in the output layer, our output is limited to two values. That neuron can output a 0 or a 1. We can add nodes to our output layer to support more output values. With 2 neurons, our network can output 4 different values. With 3 neurons, 8 different values, and so on. We can also add more nodes to the hidden layer. The number of nodes in the hidden layer does not have to match the input layer. And finally, we can add multiple hidden layers, and that's how we get a deep neural net. There is this important theorem that tells us that a two-layer neural network with a sufficient number of neurons can approximate any continuous function to any desired accuracy. That means that with enough neurons, a two-layer neural network can learn anything, any aspect of the world that can be expressed as a continuous function. That's good news. Now, in practice, the hidden layers of the network can be seen as learning and refining the features. It becomes less important that we pick the right features. The wrong features will be filtered out early. Each node in the hidden layer computes some new relevant information that can be seen as a new and more complex feature that will be passed to the next layer. Now, the problem is that as we increase the number of neurons, there is an increased risk of overfitting, especially when we do not have enough training examples. And finally, the gradient descent can still get stuck in local minima. At this point, I encourage you to go to playground.tensorflow.org and try a few things. Try how you can vary the features, how you can vary the number of hidden layers, and so on, and how your output will vary. Try a few things to get a feel of what's happening here.